So the structure pop quiz 6. Any question or doubt in the first one? The first question. Question 2, any doubt? Any doubt in question 2? Question 3. And question 3, 5.2 grams of a sodium hydrogen carbonate is added to an excess of an acid. The temperature increase and the energy change is calculated, which is 1030. What is the enthalpy change per mole of a sodium hydrogen carbonate? So if we need the enthalpy change is energy divided by mole. And we always use a limiting reagent. So as they already mentioned, that acid was in excess, so means sodium hydrogen carbonate is a limiting reagent. The energy should be in kilojoules and we'll have the mole. So this is 1030 joules. We divided by 1000, so it will become 1.03 kilojoule. How to work out the moles? Moles of sodium hydrogen carbonate, moles equal mass in gram divided by the molar mass. So the formula for sodium hydrogen carbonate is NaHCO3. So mass in gram is 5.2 and the molar mass of a sodium hydrogen carbonate, as sodium is 23. Sodium is 23, hydrogen is 1, carbon is 12 and oxygen is 16 multiplied by 3. So 5.2 divided by 16 multiplied by 3, 48 plus 12 makes 60. And then 60 plus 1, 61, and then 23 is there. It will be 84. So this will be 5.2 divided by 84. So we got 0.061 mole. 0.061 moles. And we just need the enthalpy change. So energy divided by mole. So 0.061. So we got 16.6. The magnitude, and because the energy is released, so obviously it's an exothermic reaction. So 16.6 kilojoule per mole. So it matches with option B. So B will be the right answer for this. Yes, I will explain again. Look, whenever we need the enthalpy change, whenever we need the enthalpy change or energy change, it is energy divided by the mole. The energy is 1030, but it should be in kilojoules. So when we divide it by 1000, it will give 1.03 kilojoule. So that is the energy. To get the moles, the mass in gram is given. So the formula for sodium hydrogen carbonate, what is the chemical formula? The sodium hydrogen carbonate is NaHCO3 because sodium is +1 and the hydrogen carbonate valency is -1. So the chemical formula for sodium hydrogen carbonate is NaHCO3. So we need the moles. So if you need the moles, it's a mass in gram, which is 5.2 divided by the molar mass. So molar mass, sodium is 23, hydrogen is 1, carbon is 12, and oxygen is 16 multiplied by 3. So this will be, the denominator will be the molar mass. So when we divide, we get the moles of this, which is equals to 0.0619. And we need the enthalpy change per mole, be the energy released for 1 mole. So that is 1.03 divided by 0.0619. So when you simplify, you get 16.6 kilojoule per mole. So it matches with option B. Question 4, any doubt? Question 5, any doubt? Any doubt in question 5? Specific part? 5A2. The first part is we have to complete. The first part we have to complete the table. One is the change in the mass, another one is the change in temperature. So the mass of a spirit burner before the start and at the end. So how much mass is being burned? So you just have to take a difference. So that will be equals to 0.57, the difference. And the temperature change, you have to just take a difference. The initial was 19, and the final temperature is there, which is 65.3. So when you take the difference of the two temperatures, that will be 45.8. Now, for a mass, you don't need to put a negative sign. For the mass, you don't have to put a negative sign here. Because we need the change, the difference. So this will be 45.8. The specific heat capacity of the water is 4.18. We need the enthalpy change of a combustion. So if we need the enthalpy change of a combustion, enthalpy change E is equals to, the enthalpy change is energy divided by mole. Like enthalpy change is how much energy being released or absorbed divided by the mole. Now, how to work out E? The formula for E, the energy, that is Cm delta T, where C is a specific heat capacity, that is 4.18. M is a change in the mass. M is not like in terms of not change in the mass. M is like how much water is being used. So we use 75 grams. So the mass will be 75, because what actually happened, we use a substance, we burn a substance, and when the substance is burned, all of the energy which is released on the combustion is absorbed by the water. And we assume there is no energy loss. So energy absorbed by the water is Cm delta T. So C is the specific heat of the water, M is the mass of the water, and delta T is the change in temperature of the water, which is 45.8 here. So we multiply by 45.8. When we multiply all this, we will get the how much energy. So 45.8 into 4.18. So we got 14,358 joules. But that is in joules. So we have to convert into kilojoules. So we divide it by 1000. So this will become 14.4, because if we round off, 14.3 significant figure. So 14.4 kilojoule will be there. We don't have to change the mass from gram to kilogram, because as you can see, the unit of the specific heat is given in gram, joule per gram degree centigrade. So it means the mass should be in gram. If the unit of the specific heat was joules per kilogram degree centigrade, then in that case, the mass should be in kilogram. So in the questions, usually the specific heat unit is in grams, so you don't have to convert the unit of the mass unless. Why mass of the water? Because when we burn the substance, as we discussed this part about the enthalpy change, that we have a spirit burner, we burn the substance, so substance release energy, and we assume that all of the energy is being absorbed by the water. And how to know how much energy is absorbed by the water? That is the specific heat of the water, the mass of the water, and the temperature change. Mass of alcohol is, we will use the mass of alcohol to work out the enthalpy change, to work out the moles of alcohol burned. But what is our concept here? That the spirit burner, when it burned the substance, it releases energy, and that all energy is absorbed by the water, so it causes the water temperature to change. So we always use the mass of a water. That's the rule of the energy changes whenever we want to calculate the energy change. Even for solution, even for the combustion. So this will give us the energy. And because the temperature is increasing, so means it should be negative here, or energy will be released. How to work out the moles? So how, the moles of a substance which you are burning, moles equal mass in gram divided by molar mass. So how much mass of a substance, a spirit burner, the difference in the mass is there. That will give us the mass in gram, which is 0.57. Divided by the molar mass. For the molar mass, sometime in the question they provide you the molar mass. If they don't provide, then you have to work out from the structure. The molar mass of 2-methyl propane 2-ol. So if I want to work out the molar mass of 2-methyl propane 2-ol, I should draw the structure of this. So it is 2-methyl propane 2-ol. Means we have second position, because propane means like, prop means 3 carbon atoms are there. So there are 3 carbon atoms. Second position, there's a methyl group. So if I count this left hand side as the first carbon, so second position, there's a methyl group. And second position, there's a all alcohol group as well. So OH is also there. So how many hydrogen this will have? This will have 3 hydrogens. And how many hydrogen this will have? This will also have 3 hydrogen. So this is a structure of 2-methyl propane 2-ol. Second position, there's a methyl group. Prop because 3 carbon atoms are there in the main chain. And 2-ol means second position, there is a alcohol group. So what will be the molar mass? How there is CH3 both side? Because carbon maximum can form 4 bonds. So prop means, see this prop means 3 carbon, propane. So we draw 3 carbon. Second carbon is having a methyl group. Meth means 1 carbon. And then second carbon is also having a OH. So second carbon is also having a OH. How many hydrogen this carbon should have? Because it is forming 1 bond. So how many hydrogen this should have? This should have 3 hydrogens. This carbon has formed 1 bond. So how many hydrogen this should have? This should also have 3 hydrogens. So this is a main structure. And these two are the branches. One is a functional group, one is a branch. So second position, the OH is attached, and the second position, the methyl group is also attached. So we want to work out the moles. If we want to work out the moles, moles equal mass in gram over molar mass. What about the molar mass of this compound? 1, 2, 3, 4 carbon atoms are there. So 12 into 4 or 4 into 12. How many hydrogen are there? 3, 6, 9 and plus 1, 10. So 1 multiplied by 10. And how many oxygen? Only 1 oxygen. So 12 multiplied by 4, that will make 48 plus 10, 58 plus 16. So it will make 74. So total mass, the molar mass of this compound is 74. So moles equal mass in gram divided by the molar mass. So divided by 74. So 0.57 divided by 74. What's the answer? That will give us the moles. -7.7 exponent -3. Okay. So we got the moles. So 7.7 into 10 power negative 3. Now we need the enthalpy change, or 0.007, that's, or 0.0077. So if we need the enthalpy change is energy divided by mole. So the energy which we calculated was 14.4 kilojoule, and the moles of this substance were 7.7 exponent minus 3 mole. So when we divide, we get delta H. Because the temperature is increasing, so we have to place a negative sign. So the enthalpy change per mole for this reaction, that is minus 1864. Okay. So negative 1864 kilojoule per mole. That is enthalpy change of a combustion of this 2-methyl propan 2-ol. Is it clear, this one? No, answer for this one cannot be in joule per mole. It should always be in kilojoule per mole, because the standard unit for enthalpy change is kilojoule. If it is in joules, we have to convert into kilojoule. Now, state the standard enthalpy change of a combustion can be calculated by using the standard enthalpy change of a formation. 2-methyl propane 2-ol formation is given carbon dioxide. Why the enthalpy change of a formation has stated, why no enthalpy change of a oxygen is not given? Because enthalpy change of a formation is only for compound. Oxygen is not a compound. Oxygen is an element. So, and it is in standard state. That's why the formation is always 0. Formation of the element is always 0 because formation is only given for the compound. Now, complete the Hess cycle. So, here we have elements and calculate the standard enthalpy change of a combustion from the data and the table in the Hess cycle. So, how we can use this? So, what are the elements? We have 4 carbon. How many hydrogen? You can just balance this equation first. C4H10O is there, plus O2 gives CO2 plus H2O. So if we want to balance, first we balance carbon. For combustion equation, we balance carbon, so 4 carbon. Then we balance hydrogen, 10 are there, so we put 5, so hydrogen is balanced. What about oxygen? What about oxygen? 4 multiplied by 2, 8, and plus 5, 13. 1 is already there, so I will just put 6, so we have 13 oxygen. So this equation is balanced, the first two. Then we just have to put elements here. Then we have to put the oxygen, like hydrogen. How many? 10 hydrogen we need. So this will be hydrogen. How to have 10? 5. And oxygen we need 13. So O2, because oxygen in a standard state. So O2 we need 13. So how we can have a 13? So we can write as 13 by 2, because 13 by 2 O2 will be equals to 13 oxygen. So we can write a fraction here. That's acceptable. Now, how to solve the Hess law cycle and you can also label the arrows. As you can see here, elements are forming what? Elements are forming 2-methyl propane 2-ol. So what is this energy? This energy is minus 359. This is enthalpy change of a combustion of 2-methyl propane 2-ol, which we don't know. And this is the formation of a carbon dioxide. So what is the formation of a carbon dioxide? The formation of a carbon dioxide is 394. But how many moles of the carbon dioxide are formed? 4. So this should be multiplied by 4. Same way, this is also a formation of a water. So when water is formed, the energy change is minus 286 for 1 mole. But how many moles of the water are formed? 5 moles. So this will be multiplied by 5. Now, how to identify the Hess law cycle, the start and the ends? As I mentioned, where the two arrows are pointing out, that is always the start of the cycle. As you can see here, two arrows are pointing out. So this is a start of the cycle. Where the two arrows are pointing in, that is the end of the cycle. So if we follow route 1 or we follow route 2, the overall energy change is independent of the route or the path we follow. So if we follow this route, if we follow this route, route 1, or we follow route 2, we'll get the same enthalpy changes, energy. So it will be minus, this route energy is 359 plus enthalpy change of a combustion. And this route is minus 394 times 4 plus minus 286 times 5. And you need the enthalpy change of a combustion. So this 359 will move other side. So this will become positive other side. So this will become plus 359. Which is the enthalpy change of a combustion of using the Hess law, that is minus 2647. So delta a combustion minus 2647 kilojoule per mole. So this is enthalpy change of a combustion by using the Hess law. And when we use the practical method, we were getting a different answer. It was about like minus 1860 something. That was our previous answer. Is it clear how we use the Hess law? Any doubt in this? Okay. The next is the standard enthalpy change of a combustion, which we obtain in part A, means the practically, like in part A2, that is the practical method of obtaining the enthalpy change. Like you burn the fuel, it releases energy, and all of the energy is absorbed by the water. And using the energy absorbed by the water and the moles of a substance burned, we got the enthalpy change. That is one. The second method, we use the standard enthalpy changes, and using the Hess law, we work out the enthalpy change. And we were getting a different answer. So what are the reason why the using the Hess law is different from the experimental method? Because experimentally what will happen when we are working out the enthalpy change, there is always a heat loss to the surrounding. Our assumption is that there's no heat loss, but practically what will happen when you are burning a 2-methyl propane tool or any fuel you burn, it's not like all 100% of energy transferred to the water. So some of the energy transferred to the surrounding, so heat is lost to the surrounding. That is one thing. Another reason for that, we consider the specific, like all of the energy is absorbed by the water only. But what might happen, some of the energy absorbed by the beaker. So we did not consider even a beaker or a thermometer will also absorb energy, but we did not consider them. We consider that all of the energy being absorbed by the water, and we neglect the specific heats or the energy absorbed by the beaker or the thermometer. Another thing, what might happen, maybe when we are burning, the fuel may not burn like they're not a complete combustion, because when we are assuming that this substance is burned in the presence of oxygen, it gives carbon dioxide and water. So we assume that it is burned completely. But what if it is a limited supply of oxygen? So as a result, it might produce a carbon monoxide. So definitely the enthalpy change will be lower, because when a formation of a carbon monoxide occur in an incomplete combustion, the enthalpy change is always lower than the complete combustion with the production of a carbon dioxide. So these are some reasons why the enthalpy change may not, the practical enthalpy change may not match with the theoretical enthalpy change, which is calculated by the Hess law. Is it clear? That's all. So that was the last question.